Hi all. Today I'll be presenting our paper Scalable but Wasteful Current State of Replication in the Cloud. This work was done in collaboration with Aleksey and Abutalib. So strongly consistent replication, it's currently everywhere, and it's the backbone of modern cloud services ranging from cloud data stores to configuration management. And in order to ensure this strong consistency, all these services implement state machine replication primarily using consensus protocols. So henceforth, I'll be mentioning them as replication protocols. Okay, so one of the main objective of these replication protocols is to achieve high throughput. Few examples of such cloud services and cloud data stores are Google Spanner, Yogabyte DB, Cockroach DB, Zookeeper, and many more. So how do these replication protocols try to achieve this high throughput? Let us consider a simple example of a replication protocol like multipaxos. As you can see in the image, in the case of multipaxos, the leader does most of the work by talking to the clients and also trying to replicate their requests. And at one point, it becomes a bottleneck of the system. So how do we optimize a replication protocol like this? One way to optimize this is to shift the load. Many protocols use this approach to shift the load from the bottleneck node to the underutilized nodes. A few examples of such protocols who try to shift this load are ePaxos, SDPaxos, and PIGPaxos. And each of these protocols have a different way of shifting this load. So here we see how ePaxos is trying to shift the load and utilize more resources to achieve this high throughput. So let us now talk about the resource utilization of these replication protocols and how do they actually differ from each other. In order to do that, let us consider a simple example of taking three dedicated nodes with two cores each. And we will try to run an instance of multipaxos and ePaxos, and let's look at the resource utilization. So when we run an instance of multipaxos, we see that hypothetically, uh, the leader occupies both the cores, but in the case of followers, they occupy only a single core, leaving one idle. Now, when we compare this to a complicated protocol like ePaxos, we see that it tries to shift the load and remove the bottleneck by shifting the load. And in doing so, it actually ends up utilizing all the cores and hence achieves high throughput, which is great for ePaxos. And this optimization helps in achieving very high throughput. That's great. So let us now look into this throughput increase and resource utilization. So we started with first confirming the performance gains of ePaxos protocol. So for that, we started with a simple experiment by running an instance of multipaxos and ePaxos with 50% write workload and targeting an in-memory key value store for about 60 seconds. And in this graph, we show the per second throughput over the course of our experiment. So as you can see from the graph, multipaxos achieves around 14K throughput, but ePaxos ends up achieving 18K throughput, which is about 20% higher, and it's in the similar ballpark as the ePaxos paper. So this is great for ePaxos achieving this very high throughput. But where does this performance gain actually come from? What's the missing piece which is not discussed? So this performance gain comes at a cost of resource efficiency, and this is nowhere discussed. So for the same experiment, we now look at the CPU utilization. And in this graph, we see that in the case of ePaxos, all the nodes hit a peak CPU utilization of 100%. Whereas when we compare this with multipaxos, we see that only the leader hits a peak utilization of 100%, and all the followers hit a peak CPU utilization of around 25%. So here we see that ePaxos with 500% utilization achieves 18K throughput, but multipaxos with just 200% utilization achieves 14K throughput. So clearly multipaxos shows better resource efficiency when we compare that to ePaxos. In order to better analyze the resource efficiency of these replication protocols, we introduce a new metric, which is throughput per unit of constraining resource utilization. We say constraining here because we see that resource is clearly the bottleneck of the system, and this constraining resource, whichever it might be, inhibits the scalability of the system. So in our case, in our experiments, we consider only the CPU utilization, but other factors like memory, network bandwidth can also be used as factors for analyzing this resource efficiency. So what does this metric do? This metric helps in determining the added cost of shifting the load and removing the bottleneck for these replication protocols. So let us now look at how this metric actually works for our previous experiment. So in this graph, we show the normalized throughput, which is throughput per unit of aggregate CPU utilization, which is our constraining resource in this case. And we see that multi-Paxos has better normalized throughput when we compare it to ePaxos, which is great. Okay, multi-Paxos has better resource efficiency. But why do we even care about resource efficiency? Why does it actually matter? So resource efficiency matters because all these replication protocols are actually deployed on cloud, which is pay-as-you-go utility model, and we need to be aware of the amount of resources we actually end up utilizing. And we have seen the replication protocols like ePaxos earlier, which try to optimize by shifting the load from the bottleneck node to the idle resources. But these optimizations are done keeping in mind that the machines are actually dedicated. In reality, all the databases are actually deployed on cloud where resources are generally packed, leaving very limited to non-idle resources for these replication protocols to be utilized. Okay, so a few examples of such cloud databases like Google Spanner, Yugabyte DB, Cockroach DB, and many more are generally sharded, and they deploy a replication instance for each shard. And many such replication instances are generally packed together in cloud on the same physical machine. Okay, to explain this better, let us consider a simple example of packing. So in this case, we consider 5 nodes with 6 cores each, and we will try to pack multiple instances of these replication protocols. So in our case, we'll specifically try to pack multiple instances of multi-Paxos protocol. Okay, so here we try to pack instance 1, and we see that the leader occupies 2 cores and followers occupy 1 core each, similar to what we have seen earlier. So, and moving on, when we try to pack instance 2, we see that the leader here is in machine 2, and and the reason for this is due to many reasons like fault tolerance, high availability, load balancing, etc. And we see in the same format that the leader occupies 2 cores and the followers occupy a single core each. So moving on, we try to pack instance 3, instance 4, and instance 5 in the same manner. And here we see that all the machines are completely packed and there are no additional buffer of resources available for these replication protocols to utilize in this case. And now we perform a similar experiment where we try to pack 5 instances of these replication protocols on larger machines with 50% write workload targeting an in-memory key value store for about 60 seconds. And in this case, we see that in the case of multi-Paxos, each instance achieves around 30K throughput compared to ePaxos, where each instance achieves only around 15K throughput. So we see this because in a resource constrained setting, ePaxos doesn't have the opportunity to utilize additional resources in order to provide this high throughput, which we have seen earlier. So for the same experiment, we now show the aggregate throughput of all the instances per second over the course of our experiment. And we see that multi-Paxos ends up achieving twice the throughput of ePaxos. And this is due to high resource efficiency. But how do we actually estimate this performance impact on cloud just due to resource efficiency? So this is where our metric comes into play. Our metric, throughput per unit of constraining resource utilization, acts as a really good proxy for the performance of replication protocols in a cloud setting. So here we now compare the two graphs, normalized throughput for a single instance on a dedicated resource setting to the aggregate throughput of instances in shared resource setting. And we see how the metric actually shows us a picture of the performance of these replication protocols in a cloud setting. And we clearly see that multi-Paxos has better throughput. So finally, we try to compare here the throughput of replication protocol in a dedicated resource setting and the aggregate throughput of replication protocols in a shared resource setting. And we see that the optimizations proposed so far for the replication protocols definitely improve the throughput, but surely ignore the resource efficiency. And in this paper, we introduce a new metric which helps in understanding the cost of these uh, optimizations and the shifting of the load. And we hope that in the future, replication protocols will be resource optimized and when they are actually deployed on cloud. Thank you.